Yesterday, starting with the any group, we produce the spaces of orders in the group, and well, suppose that the group is orderable. So we have a non-empty space of left orders, and inside there might be some other space. Other spaces, the space of by orders and the space of congruent left orders. And what is important is that these three spaces have natural topology. They are always compact. There is a natural action by conjugacy or by translation of gamma on the space of left order. And of course, there is an action of the space of the group of automorphism of gamma on the space of left order. It's very useful to look at this. So let me just come back to this. So whenever you have an order and a group element, you get a new order that I will denote this way. And for this new order, an element is larger than another one. F is larger than G, if and only if the conjugate of F is larger than the conjugate of G for the original order. Okay, this is the definition of the action, and this is an action of the group gamma on the space of left order. And this is not a good picture because the space of these spaces are totally disconnected, but here we have the space of left orders. Inside there might be some congruent left orders, and inside the congruent left order there might be some by orders. And the point is that the thing is that the by orders are the fixed, okay? And the reason is that this is an action by conjugacy, and by orders are exactly the left orders are invariant by conjugacy. Okay. And another thing which is important to point out is that, well, congruent orders are not invariant under actions. They are not bi-invariant, but the subspace of congruent order is invariant under. Not pointwise, but as I said. So CLO gamma is invariant under this. And this is very natural, but I will give the argument because in order to refresh what is the action and what kind of things you have to prove in order to show this. So I have an order which is congruent, and I take a group element H in gamma, and I want to show that the image of this order by H is also congruent. To show that an order is congruent means that I take two elements, positive element F and G, and I have to show that FG to the square is larger than G. So I have to show that if F is larger than the identity for this new order and G is larger than the identity for this new order, then FG to the square is larger than the identity. Is larger than G for this new order. Okay. But now, so this is what I want to, what I have to do. But now the point is that if I do have this, then, well, by the definition of the action, what I have is that the conjugate of F by H larger than the identity for the original order because of the action, and the conjugate of G by H is larger than the identity. And since the order was congruent, I have two positive elements, so the first times the square of the second is larger than the second. And this is just H F G to the square H inverse larger than H G H inverse. And again, because of the definition of the action, this is saying that F G to the square is larger than G with respect to the norm. And this is exactly what I need to. Okay. Okay. So I get a new order, starting with a congruent order, I get a new order, and the new order is also. So there is some dynamics here in the subspace of the new order. It might be very large actually. Adam proved that if a group has no free subsemigroup, then every order is convariant. So this applies, for instance, for nilpotent. And in more nilpotent groups, the space of left orders is a Cantor set. So there is a invariant set. There is a Cantor set of convariant left orders. Okay. Okay, so this is the kind of thing that I want to add. Okay, so I don't have to use this other class. Yeah. Sorry. Yeah. This is for me. Okay. Well, I want to give the ideas, not the full proof, because it involves some structure theorems that I will somehow, I would say boring, but the key idea is very, very nice. So this is a theorem by Peter. It says that the space of left orders of any group, any left orderable group is either finite or uncountable. Actually, it contains a copy of the Cantor set. It is infinite, then it contains a copy of the Cantor. And actually, you don't need any kind of cardinality assumption of gamma, but let me focalize on the case where gamma is say finitely generated. Okay, let me before giving the idea, the rough idea of the proof of this, let me just say that this is false for bi-orders. We got discussed by Adam in the other session. So there are examples of bi-orderable groups but countably many left bi-orders. But this is true for Conrad or Conradian orders in a very strong way. Okay, and this is a theorem by Richard. So assume gamma is, say, countable. So the theorem is that the space of Conradian left orders on gamma either finite or a Cantor set. So in general, the space of left order contains a Cantor set because infinite, but here it is equal to a Cantor set. This means that there is no isolated point in the space of left. Okay, so remember, the space for the case where gamma is countable, the space of left orders is metrizable. So that it is a Hausdorff totally disconnected from the space. The only thing we have to add in order to get a Cantor set is no isolated point. So what we have to prove is that there is no isolated point in space in left order unless there are only finitely limited. Okay.
Yeah, it's uncountable. No, it's not uncountable.
No, gamma is
If it is uncountable.
Gamma finitely generated.
If it is uncountable, then you know that it's not uncountable.
If it is, yeah, it should be. Yeah, I think that if you take that's a good question. Is C to some very big cardinality? I think that is special. Because yeah. Sounds big. So this. I think this is an example. The space of orders, by orders, left orders is the same here. It's not the best. Okay. It should be true. So for me, I will focus on the case where gamma is finitely generated. Okay, let me stress this because
So gamma will be counted.
so I finitely generated.
Yeah.
It's better because in case of where gamma is finitely generated, there is a canonical geometric in the space of questions. So you have to choose the system of generator, but if you change the system of generators, you change the metric of the space of left orders in a bi-Lipschitz way. So there is a kind of natural equivalent class of metrics in the space of left orders. And by the way, the point is that I should keep in mind that orderability is a local property. If you want to show that some group is orderable, you only need to check that finitely generated subgroups are orderable. You show that every finitely generated subgroup is orderable, then the group itself is orderable. It's a kind of another component kind of argument. This is Barnes scale, but actually it's also the component. Okay, so from now on, I will concentrate on the case Barnes scale. So let me just before showing this, let me just say that this alternative is false in the case of a space of Lefort. There are groups such that the space of Lefort is uncountable, but has isolated points. Something very strange. So some counter sets and where there are some other that are isolated. So the example here, so this is actually the first example in the literature, quite amazing. So this is the first example. And then gamma equal to the break group in estimates. So there is one order which is isolated, and there are many others that are non-isolated. Let me describe both of them. So the isolated order, this was discovered by Dubrovin and Dubrovin. There are many extensions of this construction in many directions by itself, play, renewal, and I'm completely sure that I need some names here, so I will put some dots. Okay, because there are many examples. Okay, sorry. There's also Matsumoto. Matsumoto? Well, different example. Yeah, Matsumoto. Just really yourself, no? No. Okay. For me, sure. I mean, no, but the point is amazing because for some time people believe that such a thing was impossible. But there are a lot of they are combinatorially very surprising. So this is the way I like to see B3. So there is what is B3? So this is the group generated by two elements. Let me give the canonical implementation. So this is okay. So this is a presentation. This is the classical presentation. Okay. But now I will change the generator. So you take A, sigma 1, sigma 2, and B, I think take sigma 2 inverse. Okay. And doing this, I get the following presentation. So this is generated by two elements, and this is B, A squared B equals to A. Let me check whether this is sorry. This. Okay, so let me just check. So B is sigma 2 inverse and A is sigma 1, sigma 2. So B A squared B equals sigma 2 inverse sigma 1, sigma 2, sigma 1, sigma 2, sigma 1, sigma 2. Okay. Well, this is equal to sigma 1, sigma 2, sigma 1. I can change it by sigma 2, sigma 1, sigma 2. So I have a sigma 1 inverse here. That's okay. So something wrong. Yeah, there are too many. Okay. So this is. No, I made a mistake here. No. Okay. I understand. This is Okay. Now, what is nice here is that this presentation is very special. It looks like the presentation of the clay bottom group. So remember, the clay bottom group is generated by A and B, and you get the presentation, the conjugate of B by A equals B inverse. That this may be written as B A B equals A. And here I have the same relation. And now the point is that the Cayley graph of this group, with these generators, is something very nice. Okay? So I will draw the Cayley graph. So something like so. This is so I have to draw the oriented Cayley graph because I am dealing with positive and negative direction. So this is going to be the identity, and in this direction, these are multiplication by A. And well, starting from here, we will be the multiplication by B. But now the point is that this is multiplication by B. And now I have this relation B A B equal to A. So this is saying B A B equal to A. So this is the direction of B. And here, again, I have B A B is equal to A. So B goes up in this at this level, it goes down here, it goes up here, and so on. So if you look at now the graph, you will see that the clay bottom group has this decomposition that I gave yesterday. Because every element which is in red here is a product of positive powers of A and B. Okay? And every element which is in blue now is a product of negative powers of A and B. Okay. And as I explained yesterday, this decomposition implies that the order for which this is the positive form is an isolated point in the space of the form. Well, it turns out that amazingly, the same happens. So B3 is equal to the decomposition of so decompose it into these two semi, which are finite. And it's a nice exercise to draw the Cayley graph of the extremes with cardinality. Because there is something like this that the Cayley graph is more complicated, but half of the group is covered by positive powers like A and B, and half of the group is covered by negative powers. Okay, well, so this gives an order, which is the ordinary order, which is isolated in the space of the form. The order for which this is the positive form. Because if you have another order for which these two elements are positive, well, the orders have to be the same. Okay. Now, there is a difference between the gray group and the plain bottom group. Is that for the plain bottom group there is also the decomposition. There's also this decomposition. So you can mix the positive and negative powers of it. And this is no longer true for. And the reason is that in this tree there are many orders. If this was true for this, as I explained yesterday, it's implies that there are only 4 left orders from the claim of the group. If this was true also in the tree, that would imply the same thing. That would imply in particular because of the very classification that is resolvable, it is not true. So this is not true for me. So we cannot this is not that. And actually there is it is more than an unisolated point. So it's an order on the tree with a very rich dynamics. So what that means is that it means that there is an order for which the orbit, the closure of the orbit is a Cantor center. And this is a little exercise. In order to show this, it suffices to show that there exists a sequence of elements in the U, such that if you conjugate the order by these elements, then you converge to the original order, and all these conjugates are equal. So this is what is called in the linguistics. This is a recurrence point. It's a point which is an accumulation point of solving. Okay? Whenever you have this, well, the person of the order is a kind of circle. You can accumulate any point in the order. So all the points in the order non-isolated, so this is a kind of circle. And the order is the there are many orders on the tree that do this stuff, but the order is the Hormoise order. The Hormoise order has this property. Okay? And what is the Hormoise order? Now I use the standard generators, and I say that an element, so the positive one of the Hormoise order is this. There are two kind of elements. There are elements of the form which are power of sigma 2, and elements of the form sigma 1, and 1, sigma 2, and 1, sigma 1, etc. Where the only condition is that the powers of sigma 1 are positive, and there is no condition for the power of sigma. Okay? It turns out that this is the positive form of so this is highly non-trivial. So one has to prove two things, that every element in the braid loop belongs to one of these, and one has to prove also that these two sets are disjoint. This is not always. So it may happen that the inverse of an element like this, because of the relations, can be also written this way, but actually this is not. Okay. Okay, these are the examples. So showing this is not not that easy. So anyway, this is the first example in the literature, but as I mentioned, there are many examples today, many generalizations in many directions. But the question that I had that I was is it true that for a generic, in some sense, left orderable group gamma, the space so for a generic left orderable group, the space of left orders is a campus. Okay, that should be natural to expect. So in order to have this kind of isolated orders, we really need something very specific combinatorial properties. So I guess the empiric doesn't agree that anyway. So this is a question, not a conjecture. And also, you can change the notion of genetics. You can say, well, genetics means this. Okay. I'm joking. Okay, so this is a natural question to ask. So let me come back to the theorem of limit. You see that there is some dynamics. There is always some dynamics on this, and it is always interesting to look at it. So, for instance, in order to show this, in order to show that there is a kind of set, there is dynamics, because there is the reaction of a sequence of new dynamics, and we can draw the result. So, idea for the proof of limits. Okay, so you have the action of the group on the space of left orders. So I will assume that again gamma is finitely general. So I don't need it. So what is important is whenever you have a group action, there is a classical argument using Thorne's lemma that says that there is a minimal invariant set for it. Okay. Take a minimal invariant non-empty closed set for the. Okay, the way of proving this, I think you really need. If you generally to show this, you really need some syllabus. So you take the family of all closed invariants, non-empty subsets. You apply some level. There is some minimum. Okay. The point is that since this space is compact, any change of invariant compact subsets, subset which is invariant, so you just take the intersection. So this is totally interesting. The important thing is that we're considering subspaces which are not empty, and well. Now take the set of accumulation points. And the point is that this is also invariant under the group R. Because this is something that I mentioned yesterday, I think that the action is it's an action by polynomials. So if you have a set which is invariant, the set of accumulation points is also invariant. But this is a closed set. And this is contained in them. Okay. So there are only two possibilities. M was minimal. Okay. So the possibility is that M prime equals to M. And the other possibility is that M was minimal among subsets which are not empty. The other possibility is that M prime is empty. When you have this, I think you have a kind of set. Because, well, in this case, we're inside an advisable space, totally disconnected, all points are accumulation. We have a kind of set. So the difficult case is this. I mean, difficult. This case was already done, was done by Venko in another language, but actually it was already. But the point, so I will not give the complete proof in this case because, as I said before, it's somehow boring because you have to go into some structures. But the point is that the following lemma, you will see that again the convariant property will appear as a fundamental property. So the situation here is like this. So there is some. This means that M is finite. So there is a finite number of orders. 34. And the action per moves is so. If you take another here, you take an element, you get a number of here, and here, and here. And this is for every element. So the point is the following: if there is a finite orbit for the action of gamma on the face of the orders, then well, a finite orbit means finite number of orders. Then all the orders in this orbit is finite. Okay, so remember, a fixed point for the action is a bi-invariant order. Now I am in the situation which is almost that one, so there is a finite order. In that case, the orders in the orbit are combined. So you get immediately into the case of combined electrons and but let me give the proof of this because it's very simple. So take an order in the orbit and take two positive elements, F and G. Positive. So again, I have the order, and the orbit is finite. I will look at the action of G in this, action of G inverse. So G inverse may be here, then here, that it has to go back. Okay, there is some n such that the order obtained by the action of G to the minus n is the same as the linear. Okay. Now F was positive for the original order, This means that F is positive for the new order because it is the same order. Well, this means that the conjugate of F by G to the minus N is larger than the identity for the linear order because of the definition of the action. And if you multiply by G to the N on the left, we get this. Okay? And G is positive. So we have this. So I got the inequality F. So there exists some N such that F G to the power N is larger than G. Which was the weak definition of the contrast property. This is what Adam said sometimes it's better to work with the weak definition of the contrast property, and sometimes it's better to work with the definition where it's okay, so what I detected is a Conradian order. And when we have a Conradian order, we have this structure of jumps. Right? Every element there is a jump. And the portion is by orderable, and the portion actually embeds into the real. So for every non-trivial element, there is this J of F and J of F. This is the smallest convex subgroup containing F, and this is the largest convex subgroup not containing. And with respect to the order that I detected, which is Conradian. So and Conrad theory says that the smaller subgroup is normal in the larger subgroup, that this is bi-orderable, and actually this is Archimedean. And therefore, this embeds into the real because of Holder's theory. Okay? And now the point is that, well, it has a Archimedean image here. And what I claim is that the Archimedean actually has rank 1. And why is that? Because if it had rank high rank, say rank 2, say if it is isomorphic to C2, then on C2 we know already that there are many left uncountably many. And we can pass any order we had in the group with this order here in this portion. And that way we get uncountably many left orders. Okay? This is the kind of argument we can find in the work of Stenhoff in order to finish the project. Here we are only detected one Conradian order, but we know also that the space of left order is. We are assuming that. So, if so, the argument is like this. There are many extra arguments, and the point is that in case gamma is not a Tararian group, there are natural and elemental procedures to produce uncountable many. Actually, uncountable. But some of these are not of a dynamical nature. We reduce to the case where some order is Conradian, and this is very useful for the rest of the group. But actually, these kind of arguments saying that the rank of the quotient has to be equal to 1 and not higher is a non-dynamical argument. Okay. And then one has to show that if you have a couple of convex jumps, the quotient is not bi-orderable, and this is the kind of thing that appears in parametric classification. Okay, but this is the key idea. Again, is to look at the action of the space of orders of the group on the space of orders and get a minimal subset. And in case this minimal invariant subset is a finite orbit, it means that there is a finite orbit, it's a cardinal order, and so on. Okay. Again, there is some extra work there, and but again, this is the boring part of it. Now I wanted to finish by looking at something which is important. So, we try to compare the space of orders with somehow the space of actions on the line. Okay, so again, I will concentrate on the case where gamma is finite infinity. And in this case, there is a control proposition that says that this gamma is left orderable only if gamma embeds the group of homomorphisms of the groups. Okay, this is very nice, but actually, it's very useful to look at the proof of this, because somehow the way of proving gives a canonical kind of maps between orders on gamma and actions on the group. Okay. And sometimes it's better to look in order to understand a particular order on gamma, it's better to look at the action. And vice versa. Okay. So let me go again to this. So assume that gamma embeds into the homomorphism of the reals. This is French. Okay. The group of homomorphisms of the reals and fix a sequence, say a dense sequence of real numbers. It's n, and say that f is larger than the identity. Or you may fix several points, but the first time that f doesn't fix a point of the sequence, it moves the point to the right. Okay? Something. Look at the graph. So I like to draw pictures here. So this is the picture of an f, which is positive for the order inducing from the action and the sequence. So we take x1 here, so f fixes this one, x2, f fixes this one, x3, etc. But for the point xk, at this point, the graph of f is above the diagonal. Okay? This is a positive. And again, this order depends on the action and the sequence. If you change the sequence, you change the order. It may happen that for the action, there is some free orbit, which means that there is a point which is only fixed by the identity. If this is the case, you just need to compare homomorphism at this point. You don't really need a full sequence. You just need this point. Okay? And this happens in many cases. Okay? But in general, if you want to order a subgroup of homomorphism, you really need to go to a. Okay, in the other direction, there was this procedure of if you start with a group, which is left orderable, so you start with a group and left orders on the group, then you put the group on the real line in an ordered way. So there is some map, say phi, from the group into the reals, which is only order preserving, with some extra properties in order to get at the end some action by homomorphism. So I don't need the precise formula. So you take it. So essentially, if you take P of f and phi of g, and if P of g is to the right of P of f, this means that f is smaller than g for f. Okay. And I like to do this map. I like to put that the phi of the identity is equal to the origin. Okay. Just for convenience. And the action of here, so gamma acts on phi of gamma in an obvious way. So the action of H on phi of F equals phi of HF. So the action of an H is like this. And if this point is the image of this one, which means that this is the point P of H. And with a careful choice of the function phi, this extends information by the models of the data. Okay. No, this action. So this action is only defined on the subset of the real line. So this action extends to the real line. Okay, not always, but in case of where the points are used in an applicative way, this exists. Continue. Okay, but now look at this action. It's very, very special. So since I say that P of the identity is equal to 0, if I have an F for which phi of F is larger than 0, well, this means that phi of F is larger than phi of the identity. Okay, but phi of F, because of the action, is F of phi of 0 of the identity. Sorry. And again, this is equivalent to that F is positive, because this is phi of the identity. Okay, so the only thing that I need to look at in order to determine whether an element is positive or not is to look at the action of an element at this point. If it moves to the right, then the element is positive. If it moves to the left, then the element is negative. This point it has a free orbit for the action. So for this action, I don't really need to go to a sequence in order to reconstruct the order. I just need to pick this point and I reconstruct the order. And this is really very, very useful. Because this is the heuristic. There is somehow some map from the space of left orders into the space of actions. But then it is not canonical because here it depends on the sequence, here it depends on the function and so on. But this is just an heuristic. So here there is the natural topology in the space of left. And here there is a natural topology in the space of actions. The compact topic topology. It doesn't work like this, but more or less this is the idea. The compact topology means that you care about what happens in a finite window of the real line, and you don't care what happens and this correspondence is somehow continuous. If you have an order which is very close to another one, then the actions look the same, the finite window. If they are different, they do different things. So there is an element that moves the origin to the right for the action associated to one order, and to the left for the action associated to the other. Okay, this is the idea. So writing this carefully requires work somehow. It's boring, but
you can make that precise. I mean, you can say that there is a point. No,
because
so this stays in our.
It's really easy because here you really have a compact topological space. The space of actions on the real line with the compact topology is not that good. It's not compact.
Oh,
there is some we can consider some
but is it possible
actions. But this is just an idea to prove many things in order to create an order with the action. So the idea is I have an order. I look at the action and I will try to perturb the action and then to recover a new order. And this works perfectly well to prove that, for instance, the space of left orders of the free group is a Cantor set. Okay? And this is the idea. So again, this is a theorem by McLeary in the 70s it proves a little bit more than this. In another terminology. So he proved that no left orders on the free group is determined by finitely many inequality. There is no finitely determined left order on the free. Because at that time there was no kind of. But this is equivalent to the fact that the space is random. And the group works more or less as follows. You will see the image. Right in the details is some worry. Take a left order on the free group. Take a left order, take this action, which is called the dynamic organization of the order. Any dynamic organization. So you take any function phi and so on. You look at the dynamic organization. So this dynamic organization is given by the graph of two maps, which are the generator of the free group. Now do any perturbation of the maps, perturb the generators, and get a new action. And when you have an action on the real line, you can produce an order. You get a new order. Okay. And now the point is, if this perturbation is small in this topology, so you didn't change nothing on a finite window, then the new order is very close to the original one, because of this behavior that respects somehow the topology. Okay. So if you prescribe finitely many inequalities in the free group, you can see these inequalities in a finite window, and you don't change the action on this finite. So you see the very same inequalities in this finite window, and you see the same inequality. But the point is that you are allowed to do anything close to infinity. So you can change dramatically the action. And that would mean that somewhere the order has to change. Okay. So what you produce is a new order which is different from the original one, but which is very close to it. Okay. And I didn't put my hand on any order on the field. Nothing. It's just a okay, but actually there are two extensions. One of them is yeah, you have to take care of it. Yeah, you have to take. So I said there are many details to be checked, because if you do a perturbation, maybe the new action is not faithful. This is not really a big problem. Now you really need to ensure that the perturbation is strong enough, close to infinity, in order to really produce a new order. But actually, if you don't produce a new order, that will mean that you have an action which that all the actions which are close are actually conjugate. And this is impossible. If you look only finite at a finite window of the action, then you will have the full information of the action. This is nonsense. Okay, but okay, you have really to write down the data. So this is the. But actually, this works only for the free group, because if you change the generator, you start with an action of any group and you change the generator, then you kill any algebraic relation. But there is a very nice observation by Rivas that this works for any free product of any two groups. Okay, and the idea is very nice. So we have gamma 1 and gamma 2, and you cannot do this. Otherwise, you will do everything. So you take gamma 1, and instead of taking gamma 2, so gamma 1, for gamma 1, you keep the action. And for gamma 2, you conjugate the action. By some homeomorphism. In that way, you keep the action of gamma 1 is the same action, so you get all the algebraic relations in gamma 1, you keep them. Since the new action of gamma 2 is a conjugate one, you also keep all the relations in gamma 2. Then you have to prove that with a good conjugacy, what you get is actually a copy of gamma 1 of the pattern of gamma 1 and gamma 2, and you can try to Yeah, it's direct in a very big window. And then you have to change the diagonal. But this is again, this is a myth. Putting the on this is somehow again somehow worrying, but again very close. Okay, you have a product of two groups, and you keep the action of the group, and the action of gamma 2, you just conjugate it. Okay, and you put them together again on the line, and you get a new action on the line of this product. You get a new order, and you put that this new order will be very close to the one because that's nothing on a window. And actually it is different if 5 does something very, very strong. Okay, this is there. And the last, no, this is because I am out of time. So for this afternoon, I will show this is a theorem by again on theory that there exists dense orbit in the space of left orders. Okay. So I will use that here. Okay, so I will start here. No? Do you know something about the amalgamated project?
Sorry, I didn't hear you. Oh, you can produce isolated points, or you can get.
You can produce
Like, I think of the horizontal groups. Z, amalgamated over Z, and then you have isolated points. Yeah.
The results for one related. There are results for one related. One related. Yes. The only one related
For this group,
yeah. There is some. So this is yeah, but this is not completely true. So the goal is proving that if you have a one related group, not that parallel group, then the space of left one is the campus. It's almost done, but that is not perfect.
Of course, not with that. Not made it with that. That's one way.
Okay.
I think I misread the example.
I'm going to say,
That's one later, and these be that I think it's not.
yeah, no. You're right. The way that you're discussing the individual about that, that's really no, wait, no, you're right. We're thinking. Okay. There is a theorem for one value. I think that if you take a gamma and one relator and function free, then it is locally indicable. This is Brodsky. Well, this is like that it is okay, this is true. We have to deal with others. Okay, we can discuss this because I don't have that. But what is known is that the left orders of the phi one of a surface, this is a Cantor set. Okay, so that's this for me, no? This is not all of
Great. Well, if there are no more questions, so let's.